So I thought, right in this talk, I'm going to be talking about enabling visual understanding of this one underwater scenes. And there's a work done by my PhD students, Nisha Varghese and Ashish Kumar. And there's also a project that was sponsored by by this one, DST India. And I, of course, acknowledge the support from the organization. Let me just start by saying that when we talk about underwater vision research, I mean we are faced with faced with um, okay, challenges of several kinds. Like for example, we know that there is absorption, there is scattering, which kind of leads to a distortion of the color, low contrast, blurriness, and kind of things like that. Then of course we have also lighting conditions that could be non-uniform. Then you could have suspended particles. Then there is also a scarcity, right, in terms of what you can acquire underwater. It's not like what you can do right in air, right? As opposed to that, even acquiring underwater data is not easy, and therefore, right, that also that also is a kind of a separate dimension in terms of what you can do with underwater images. And then in terms of the ground truth, right, that is also very hard. I mean, even if you take a LiDAR down, it's not really as good as what you get outside. And of course, it's not anyway a cheap option. And we are looking at vision-based kind of research, and therefore, right, even having ground truth depth predictions or the ground truth image data is not easy. There's also a big domain gap, in terms of the methods, right, that we typically build for in-air images. They don't. I mean, if you directly apply them to underwater images, they kind of seldom do well. And the last thing, right, that I also wanted to mention was that we want something which works in real time. I mean, as far as we can, right, we would like to have a method which is actually real time. So by kind of enhanced visual understanding, what I mean is, I mean, there are so many downstream tasks, which require an image which is of a high quality, and because of the fact that underwater images typically suffer from all kinds of things, low contrast and all that, blurring included, and low light and all of that, and therefore what typically happens is that if you try to do tasks like segmentation, salient point detection, edge detection, and key point detection and things like that, then you kind of typically can show that what you get as output, right, from these for these downstream tasks, you will definitely get an improved output if you were to do a restoration first, because of the loss of color, because of the loss of so much of loss of the contrast, and it's all that stuff. Now, you also need depth, for example. So the previous task, right, would not really need depth, but then when you want to navigate, right, when you have a robot, something, an underwater vehicle, unmanned vehicle that is going around, in addition to the image, you also want to know where you are, know where the other obstacles are in front of you, and that also means that you need a depth map, which should be actually good. And we know that predicting a depth map given a bad image, a degraded image, as you would get typically from an underwater camera, right, will not be an easy task. And again, right, one would like to get both a restored image as well as a depth map, right? So this entire talk is about how do you enhance visual tasks, right? I mean, or in terms of your visual understanding of the scene by actually recovering a cleaner image from a degraded image, as well as a depth map, right, which is actually enhanced, or which is more accurate, right, as opposed to what you would get directly from a degraded underwater image. And we know that, right, there are so many applications of this, including biological research, archaeology, environmental monitoring, and so on, underwater robotics, to mention a few. Now, I'm going to kind of talk about one of the works that we did recently, not so very recently, but in ICCV 23. So I'm going to summarize that work, and I'll give you a good sort of insight into what went into that work. And then, if possible, I'll also gloss over our recently accepted paper at the upcoming CVPR. If I get time, I'll also gloss over that, just to say something more on underwater that we are doing right now. But in any case, right, so in this talk, I'm going to be focusing more on a self-supervised monocular underwater depth recovery, and then a restoration, and a real sea, this one, a data set. So this paper was important is important from several aspects, in my opinion. So for example, the key objectives were that what we found was, as I will talk right down the line, that either you had methods that were doing good depth map kind of prediction, or you had algorithms, which would try to restore images. So we wanted to do a dual task, which will be like getting both at the same time, and in a manner that one aids the other. and then simultaneously in real time. And also we wanted it to be really fast. We wanted a method that would work in real time, because most of the methods that were out there were not really real time, especially, but there was none that was doing both together. And we actually took it upon ourselves to do something that would be interesting in terms of both depth as well as image restoration. And what did we do? So the motivation stemmed from the fact that, existing data depth estimation methods, if you just focus on depth, they either use haze or they use geometry, but not both. And there was not a single, deep network that could output both a restored image and depth map. Then there was no real pad data. I mean, right? I mean, even today we don't have pad data for underwater restoration that you can do in a supervised way. And then we also realized, to a surprise, that there were no underwater video data sets, which could probably be utilized, in terms of extracting, extracting view geometry and so on. So we went ahead and this is a proposal, right, that we had in that work of ours of IPCV 2023, where we actually proposed a network which we call which is actually an unsupervised, which is underwater self-supervised recovery of depth and image. I mean, that's what this use ready net stands for. It interestingly utilizes cues from both haze and geometry for underwater depth estimation. As I said, simultaneously outputs both depth and the restored image. It is completely self-supervised in the sense that we don't need a ground truth at all. And as we know, I mean, it's not also easy to get a ground truth, especially in underwater situations. And then, in addition, we actually proposed a real underwater video data set for the first time, which we called as DRUVA. The full form is there in the IPCV paper. Basically stands for data set for real underwater video data set of real underwater videos of artifacts. I mean, that's what this DRUVA stands for. And so the SOTA, right, at the time, in whatever 1.5 years ago, was something like this. I mean, you had kind of traditional prior-based methods, which were kind of not very good because of the assumptions that they were making. Then deep learning, zero shot was very slow. Supervised methods, I mean, could do either depth or image, but then there was no real pad data. These are all very synthetically driven. And the best choice, it seemed to be like an unsupervised or a self-supervised approach, which could perhaps do both. And here is a brief summary, right? I won't go into this. This is all there in the paper. Now, let me kind of come to the method. I mean, how are we doing it in a kind of different manner? So we don't need a paired data set. We try to do it completely in a self-supervised way. And then we have a single network, right, that gives both and then real output. So to just give you a feel for what kind of time we are looking at, it's about per frame, right? It takes 18 milliseconds, which is very fast. And it combines, I mean, by the way, the deep learning as well as image formation model. So there is a network, and this network is physics inspired. So the idea, right, is that behind this network is something very simple. So the idea is that, I mean, so if you can see what I'm indicating too. So what you have is a monocular video during training. During inference time, you don't need a pair. You just need a single image. But during training time, we take adjacent frames captured using a monocular video, which is what we did. I mean, when we actually captured a DRUVA data set, we actually went with when a diver went down, and then he had a camera, a monocular camera, and then he went around about 20 artifacts, which are interesting artifacts, in shallow waters, and then he took videos of these artifacts. These are all monocular videos, and the idea was that could we reconstruct these artifacts both in terms of their shape as well as the underlying clean image using an approach, right, which we call as completely self-supervised. And in this approach, what we do is we take two adjacent frames, which we know are not exactly identical. But what we do is we have a deep network, right? We have a deep network that has different modules within it. There's one that solves for the air light, which is the top, and then there's one which solves for the underlying radiance, which is what we call the scene radiance net. And then there is something that solves for the transmission map, both the direct transmission map as well as what comes out of the backscatter. And then we also have a beta net, which is supposed to be finding out the extinction coefficients. And then given that right, we had to try and train these networks, we needed a self-supervision, right, because it's completely self-supervised. So the self-supervision losses were of the following type. So what we would do is we would expect these modules to kind of disentangle the input such that we can get the air light, the radiance, and so on. And then one of the losses that we would have in the self-supervision is to kind of combine these together using the image formation model that is down right on the slide. use the image formation model to combine them and then compare with the reconstructed image, which is I1 rec, with I1, right? That is one loss. The other loss that we have is a view synthesis loss, which we get from I2. So the other frame that we have from the monocular video, we pass it through the same SR net, and then we get a scene radiance, estimate of the scene radiance, which we call as J2. And then we know that J1 and J2 are related through a depth map as well as a rotation and kind of a translation, because the camera is continuously moving. And we have a postnet which we train such that it will solve for a six-dimensional vector, which will be three rotations and three translations. And then we use the transmission map that is estimated from here in order to estimate depth map, right? Using an analytical formulation, which we know, right? So the transmission map we know is related to the depth map through an exponential function. So we use the estimated transmission map to find the depth map, and then use the depth map to warp J2 to J1, and then this J1 hat is then compared with the J1 that was estimated from the top, right? And therefore, these are the two self-supervised losses. And there is kind of one more loss, right, which we have that I'll talk about. So really, so during training, what we are doing is we have network 1, 2, 3, and there is a Gaussian blur, which is for the air light. So I1 and I2 are two adjacent frames that are going in, and then we combine them, and these are estimated by these networks, these quantities, and then these quantities are then combined, right, using the image formation haze image, the underwater image formation model, which has an absorption component and then a scatter component, backscatter component, in order to arrive at the I hat, right? In this case, it should be I1 hat ideally. And then in the top, you get the scene radiance. And then we take the second guy, pass it through the same network 1, get the scene radiance. And then from this attenuation map, which is this e power minus of beta d, from that we get a depth map. And then we kind of push this depth map and the posts, right, which we have obtained through the postnet in order to get J1 hat from J2. Right, so this is simply a view synthesis loss. It's a view constraint, and therefore we have kind of two losses which are self-supervised, one between I1 and I hat, another between J1 and J hat. And then during inference time, right, we don't need a pair. We just send one image, and then out comes the scene radiance and then depth map. Right, so basically that is the overall idea. And the losses for the network I've already explained, right? So self-supervision 1 and then self-supervision 2. In addition, we have a depth smoothness loss, which is a very standard loss. And then there is a channel-wise depth consistency loss, which is only saying that all the channels should be estimating the same depth, right? So with this, if you kind of test this network, right, in the following manner, then what you get are kind of what you can see as an output, right, is something like this, where on the left you have the input image. So this is like a monocular video, and what I'm showing is on a frame by frame basis, right, in terms of the output, right, that I'm showing this for every frame, right, that is being sent inside, you're finding the output. So this network works on a frame basis, takes only one frame at a time. And then on the extreme right is actually the kind of depth map, right, that the camera sees. And the nearby points are brighter, and then the farther points are darker. Because one of the things that we should realize is that we don't have a ground truth for this. So we have some no reference metrics and so on, right, that you can compute. And and then some more outputs right here. I mean, these are all videos that are available if you go to the DRUVA website, which is available you can just fill up a form, a requisition form, and then you can actually download the data, which is about 1.5 GB, and it will have about 20 videos of these 20 artifacts, and then right, you can kind of build your own algorithm. So this is what the DRUVA has. It's a complete 360-degree, right? This one azimuthal view of the artifact. And on the left, I'm showing you how this artifact looks like. I mean, these are some interesting artifacts that are in shallow waters. And this is, in fact, the first ever underwater video, this one, that data set. It had to be curated and so on before it could be released. And then on the right is actually a 3D kind of a point cloud, which also tells what was the camera path, which the kind of diver took. And at this point in time, let me also acknowledge Dr. Sundaresh and his team from NIO Goa, which is the National Institute of Oceanography, who are the people who actually went underneath. I mean, me and my students were just sitting on the surface on a boat, whereas the actual people that went and then who did the diving and then who took the videos are these people from NIO. And then of course this data set incidentally can also be used for other kind of applications. And then in terms of comparisons, we did comparisons on with the depth estimation work, several of them, many recent ones, restoration, again the same. And then we have a complete set of if you see the paper, there is an exhaustive set of experiments where we actually talk about, what is the, how we do both in terms of depth recovery as well as a restoration of the red image. And these are some quantitative metrics. And incidentally, right, squid and see-through are two depth data sets which do have a real depth map, a real in the sense that, which is accurate up to a scale. And therefore, right, you can have any scale in where you can have the scale in metric to calculate how well you're doing. We trained our network on our data set, and then when we did testing on these unseen data sets, we still did very well. I mean, compared to, even though, right, we had a network which hadn't seen squid data or the see-through data. In terms of restoration methods, there's nothing like really a ground truth. What we have is only a pseudo ground truth, which is for UIEB. For the other two, for DRUVA and RUIE, there's nothing like a ground truth. So only thing is we had some, no reference metrics, which we again, compared with a whole lot of methods. And then we also had this depth and restored. I'm also showing here some outputs from images, randomly grabbed from the internet, just to show that, it is not very sensitive to the data that it has already seen, and it actually works very well. I mean, even on data sets that are not seen. Then, let me just introduce you briefly to the follow-up work, which is called Seeing in Low Light. Right, it has been accepted at CVPR 2025, for which a decision came only a couple of days ago. So I'm happy to share with you that this work, right, will be this work deals with actually low light, as opposed to the one, right, that I showed earlier. And here the idea is that, right, you have really, really kind of low light videos. And in fact, right, in this case, what we did was we took actually, we took, let me just show you. So we actually had a rig, we made a stereo rig, wherein one of the cameras had a higher exposure, the other camera had a lower exposure. And we took a stereo data, actually, I mean, again, of artifacts. And of course, several artifacts. And this video was recorded in this manner, and then based upon, and then the normal lighting that we have with a larger exposure, that is what we use as a guidance for the other camera, which has a lower exposure. And right, in this work we actually show that right, with this kind of an arrangement. And then one of the key things that we bring in is the, a Retinex model, wherein we kind of break down the radiance that you see in terms of lighting and reflectance. And then of course, you need to do a bunch of, that is a bunch of other things which I'm not explaining here because it's fairly involved. But then just to say that, the whole idea was to bring in a Retinex model into this low light kind of a situation, in order to be able to see restore as well as recover depth, again do the joint task, but then now even when the light is really low. And right, this is roughly the kind of idea, but then I'm not going to be talking about this in detail. Like I said, I'll be only glossing over this. I just wanted to give you a glimpse about how this works. So on the leftmost is actually the input video that we have actually, which is a low light video. And on the right side is actually a restored video that you get out of this particular method that I haven't talked in great detail. And then on the rightmost we have a depth map. And right, with that, right, let me also, and then right, this also runs very fast. It's about 16 milliseconds on a GPU of RTX, on a GPU like RTX 3090. So to kind of conclude, so I just talked about a recent work of ours, which is completely self-supervised, which uses only input underwater images for actually training, exploits cues both from haze and geometry for depth, and returns, of course, both depth and the underlying sort of the hopefully a clean image simultaneously. Then use ReadyNet, that is what we call it, emerges to be the best for depth recovery as well as a restoration. When we kind of compared it with a bunch of techniques, each one tailored, in fact, for depth or for image. Even it outperforms methods tailored for these individual tasks. Computationally very efficient, 18 milliseconds per frame. And then in the process, we also proposed a dataset DRUVA, right, which is now available and which is being used by more than 100 researchers worldwide. And I just wanted to tell you, which I've already mentioned, that this work has been extended now to low light images utilizing a Retinex theory. And we will also be releasing another data set, which we call the ULV stereo. So it is like underwater layer, low light video. And this one will also be made this one available soon to the researchers of that work in the underwater domain. So with that, I think I'll conclude my talk. I hope I've been on time. Thank you so much.
Thank you so much. Yeah.
So we take questions on our very exciting talk. There's one question in the audience here. Yes. You want?
So how do you evaluate for the first dataset? Is there zero depth? Right?
So the question was, how do you evaluate?
Since the predicted depth was zero depth, not actual depth.
You want to just compare?
Sorry. No problem. Yeah. Thanks for the talk. So how do you evaluate for the first dataset? Because the depths that you're getting, so there's zero depths, right?
Yeah. Yeah, so the point is, right, so with respect to the underwater DRUVA data set itself, we don't have a ground truth at all. So which is the reason why I mean, what we did was we actually checked our method on squid data set as well as see-through data set for which ground truth is available. So the kind of quantitative analysis which we have done is with respect to depth data sets for which ground truth is available. For DRUVA, there is no way to evaluate the ground truth. We can only visually observe and then sort of hope that it's doing well. But then it's not just that. For squid and see-through, we've actually compared and we actually outperformed them, as I showed in that metrics table.
Thank you. Just to follow up, so then can we use the zero depth for any other task reliably, hopefully?
Can we use?
Like your DRUVA zero depths for other tasks?
I would actually think so. For example, right, you could probably, and what we also found is that if you use, I mean, if you try to use something like a foundation model, something like a dam or something, and then if you try to run it on our say restored image, then we get a depth map which looks very similar to what we have. So that is another way to sort of verify that, right, what we have is good, and then you can still have a scale invariant metric, but then because that also is only a foundation model, so really, right, there's no ground truth in that sense. But yes, I mean, right, you can use the, depth estimated from this, right? I mean, you could probably use it in order to generate a NERF model or something. You can use it for that, or for example, right, you can use it for say comparisons, and so on.
Thank you.
Any other question? Maybe one question. Otherwise, I might ask a question. So earlier in the competition discussion, we essentially discussed how does it help? How does image restoration help for downstream other tasks like object detection and semantic segmentation? So do you think this the approaches you showed for image restoration have they been shown to make object detection and semantic segmentation better compared to other image restoration methods?
Yeah, actually, you know what? I mean, in the CVPR paper, which I've not been able to share the entire set of results, we actually showed that if you do a restoration and then that if you try to use a foundation model such as a segmentation SAM or a DAM, you can actually show that on the restored image, the output, right, which you get, the segmentation map that you get is a lot more improved, right, than what you would get if you directly use the underwater image as captured. In fact, right, I mean, if you see the paper, it is there. I mean, we did downstream tasks. We did for segmentation. We did for a depth map. We showed in both cases that the restored image is actually useful. I mean, so surely yes.
Super interesting. Is there any last question? Otherwise, thank you again for the very interesting talk, and yeah, thanks for joining.
Thank you so much. Thank you.
Yeah. Thank you, Raju.
Thanks, Uma. Bye-bye.